Hi, everyone. My name is Patrick. I'm the co-founder and CTO at SIGOPT. And thanks for joining me today. I'm going to be talking today about methods for optimizing your deep learning models. And I'm excited for this conversation because this topic is of particular interest to me. We're going to be discussing optimizing deep learning models, but in two very particular contexts. First, in the context of deep learning models that are particularly expensive to train. And second, in the context of a resource-constrained team that has limited access to DevOps. So let's dive right in. For those of you who haven't heard of us at SIGOPT, we're a pretty young company with a relatively bold mission. Our mission is to build software solutions that empower modeling experts. In our experience, having access to the right solutions can make the difference between experiment success and failure. And our hope is to make it much more likely that you, as the modeler, are successful. So what does this actually mean? We'll take a broader perspective. There are at least three critical components to any model development process. First, and most importantly, there's the domain expertise. And this is the insight that you, as experts, bring to bear on solving tough problems. This, of course, should always be handled directly by the domain experts and never be outsourced. Our goal is to give those experts, that's all of you, the chance to spend the vast majority of that process working in this space, iterating on your problem, developing your objective metric, and figuring out how it connects to your business outcomes. Second, there's a certain amount of proprietary infrastructure that your team requires to ingest, clean, transform, pre-process your data, manage the model lifecycle, all the way from development to production. This is typically handled by your DevOps team or some internal infrastructure team. There may be software solutions that assist in this process, but a lot of this work has to be custom because the problem is relatively proprietary. And third, there's the subset of repeatable tasks that I've highlighted here that are the same for every single model development process. These are the tasks that should be automated with software. And furthermore, these are the tasks that can be handled by third-party software because they're the same for every model and can benefit from SaaS scale. And this is what we provide at SIGOPT. I'll briefly go over my background. So I studied math and computer science at the University of Waterloo in Canada. Then I worked in industry at companies like Facebook and Foursquare, developing products that scale to millions of users. In 2014, my co-founder Scott and I founded SIGOPT, and we're funded by investors like Y Combinator and Andreessen Horowitz. And now today, as CTO, I'm responsible for building scalable solutions for our customers and the technical challenges of optimizing models at scale. So what's important to state is that at SIGOPT, we focus exclusively on applied AI. That is, our research and products are specifically designed to solve real-world enterprise challenges. We're not interested in just tackling academic benchmarks or problems that aren't found in the real world. But going after applied AI really introduces unique challenges. And these unique challenges are where my team spends the majority of their time. And more specifically, I think the most specific challenge that we'd address today, and one of the most challenging, and the one that holds the most value for our customers, is hyperparameter optimization. If you're not familiar with this term, hyperparameter optimization is a technique for finding the best version of your model. Finding the right hyperparameters can be the difference between a model that performs poorly and a model that can dramatically impact your business. Some of you may have heard of this by other names, like hyperparameter search or model tuning, and it can also be referred to by the specific method used. So there are naive methods like grid search and random search, and more sophisticated techniques like Bayesian optimization. At SIGOPT, we provide a SaaS solution that hosts the most cutting-edge hyperparameter optimization techniques for modelers. But as I mentioned before, in the real world of applied AI, hyperparameter optimization comes with its own unique challenges. Here are a few examples, and I won't go over each of these. They're all covered very extensively on our blog if you're interested in checking that out, where we post a lot of information about the cutting-edge research we do. But today I'm going to focus on just these last two. Lengthy training cycles, that's when your model takes an extremely long time to train. And cluster orchestration, how you can most efficiently use your infrastructure to solve these problems. And very specifically, considering these challenges for deep learning models that are expensive to train. For our customers, these expensive models often go untuned because the cost is so prohibitive. Because the standard methods could take days or even weeks, which is typically a deal breaker for a lot of these teams. And this, once again, this isn't just an academic exercise. We're seeing an explosion in the amount of compute required to train these sophisticated models. This is a chart from an OpenAI blog post recently. And in short, from AlexNet in 2012 to AlphaGo 0 in 2017, there was a 300,000x increase required in the compute to train these really sophisticated models. This is a massive explosion, but it's not unprecedented. We've seen this before. In the 1800s, as coal-burning technology got more efficient, you might have expected the amount of coal burned every year to decrease. But the opposite happened. It increased dramatically. That's because as coal became a more efficient fuel source, the demand for it increased dramatically, which offset the actual decrease in unit of coal burned. Some of you may know this as the Jevons paradox. But we're seeing the same thing here. The problem of lengthy training cycles is unlikely to be solved by hardware alone. As GPUs get faster, more sophisticated models will fill the void, and our most sophisticated models will still take a long time to train. And more broadly, these type of expensive models are everywhere. Deep learning models are being used to tackle speech recognition, deep reinforcement learning, computer vision, and much more. Each of these domains is certainly growing rapidly, but also involves these complex models and huge data sets. Because of the long time required to train even one instance of these models, once again, optimizing them effectively is difficult or impossible. So we can put this in context with a case study. With TPUs, you can train ResNet 50 on ImageNet in about 12 hours. The actual algorithm and model and times are not strictly, we don't need to know the exact ones, but this is reflective of a real use case. So if this model has 12 hyperparameters, with standard techniques, you'd need to train at least 120 instances of your model in order to find one that you expect to perform well. So in total, you're actually going to be looking at about 60 days of total compute time just to get to one version of your model that you're happy with. And this is obviously really expensive, so the question is, can we do better? And the spoiler alert is that yes, we can. And the way to do that is by tackling these two challenges. So the first of the two challenges I'll address today is training and tuning efficiency. How can you improve training and tuning efficiency for these particularly expensive models? And it's certainly an area of active research. A lot of the great minds are working on this problem and trying out a lot of different solutions. One that we found particularly useful for solving this problem, and the one I'm going to talk about today, is called multitask optimization. Multitask optimization starts with a very specific idea, a very simple idea. If we can learn from partially trained models and apply those insights to fully trained models, then we can collect information about our modeling process at a reduced cost. In this sense, when we're conducting optimization, we have multiple tasks available, and some of those tasks are cheaper than others. By training with the cheaper tasks, we can learn about how our model performs without having to wait for it to finish tuning completely. This allows us to tune a model much more efficiently than would otherwise be possible. The idea relies on relatively recent but also relatively compelling research. So there's a paper from Swirsky, Snowick, and Adams from 2012 that introduces the concept. It tested with results that point to success. Conceptually, multitask blends two techniques that some of you may be familiar with. On the one hand, it relies on this previously mentioned idea of sampling partial cost versions of the model and using those to learn about the full cost version. And on the other, it relies on the cutting-edge Bayesian optimization techniques to efficiently explore the search space with the cheap cost tasks and exploit that information with full cost tasks to solve the problem. The idea is that this approach will introduce additional efficiencies and further accelerate the training process. But once again, in the world of applied AI, multitask optimization comes with unique challenges. In this other paper, they noted that in particular, the cheaper approximations of a model can introduce additional noise and bias into the process, and that can make them more challenging to practically apply to problems. So while the technique is powerful, we have to be careful about where and when we use it. In particular, we need to use it in settings where the cheaper tasks are actually going to inform us about the most expensive problem. Otherwise, we actually risk lengthening the training process because the cheap tasks can mislead us and drive us in the wrong direction. What we have found, two cases where this does perform well in practice, are defining your tasks to be subsamples of the data set, so your training is faster because you're not looking at the whole data set, or in the case of a deep learning model, training with a reduced number of training epochs. And some of the research to back that up. So here's an example that works well from the University of Freiburg, where they trained an SVM model 400 times on the MNIST data set. These charts show how the performance of the model changed with response to the two variables, the regularization parameter C, which is the vertical axis, and the kernel parameter gamma. Going from left to right, you have a 1/128th sample of the data, a 1/16th, a 1/4, and then the full data set. So what's important here is not the specific numbers, but that noting that these four charts all have roughly the same shape. And what that tells us is that in some sense, there's some information that can be learned from the cheapest model that we can use to inform us about the full cost model. That means you can learn about the full cost task more cheaply by being smart about the way you sample from the partially trained model. And that's exactly the type of problem where multitask optimization is going to perform well. We can dive into the math one level deeper. So let's say we have two functions. Here we have a blue function and a green function. And our goal is to learn about the blue function by sampling it as few times as possible. So what we can do is we can also plot the information gain from sampling from these functions. So the top blue line is the information gained by sampling from the blue function, and the bottom green dotted line is the information gained by sampling from the green function. Recall that our goal is to learn about the blue function, so that's why we see that the information gained from the green function is low. And that makes sense because we're sampling from the wrong function. Now, instead, if the two functions were correlated, whereas before they were unrelated, now you can see that there actually is some information to be gained by sampling from the green function. But it's still lower than that of sampling from the blue function, which once again makes sense. You're never going to learn more about sampling from the blue function than you are. You're never going to learn sampling more from the wrong function than you are from the actual blue function. So what's the point? Well, the point is, what if in some sense the green function was cheaper to sample from? And then furthermore, you scaled the information gained by the cost to sample. Now you can actually get into a setting where even though you're sampling the wrong function, you're still gaining information at a more efficient rate because you're sampling from a cheaper function. And that's exactly what we see here. And this is once again exactly the setting where multitask optimization performs well. So this is an area, as I said, of active research with lots of great minds working on solutions for this. Another you may have heard of is early termination, sometimes called hyperband after a specific implementation. The premise of early termination is to terminate the training process early if we predict that it will not eventually yield good results. So it's a similar method to multitask in the sense that both methods use the premise that information on partially trained models can inform our beliefs about the fully trained version at reduced cost. So the University of Freiburg again published some research comparing these methods. They present in their paper a task-based algorithm called Fabolas, a multitask-based algorithm, which has successively smaller tasks for fractions of the data set, like we saw in those previous charts. They also compare to a simple multitask implementation that has one full-cost task and one cheaper task. And here they also compare to hyperband, which is an early termination algorithm. And then as a baseline, they use two basic Bayesian optimization techniques. The comparison is done on an SVM model across 3 different data sets, which are listed here. Here are the results. So I know it's a bit of an eyeful. The goal of this test is to reduce the goal of this benchmark is to reduce the test error on these problems. And for our purposes, we're interested in seeing how quickly the given optimization method can reach that good optima. So that's the rate at which the problem reaches the y-axis. So in these problems, the green line is the Fabolas multitask algorithm. The blue line is the simple multitask algorithm. Orange is hyperband, and then we have the 2 Bayesian optimization baselines. And in every case, the multitask-based algorithms outperform the standard methods and hyperband. So now let's go from the research to the real world. As a practitioner, how would you implement this strategy? You could implement it yourself, but at SIGOP, we've made it very easy. As we discussed at the beginning of the talk, our goal is to build software solutions that are designed to empower experts. In general, practitioners can use SIGOP for hyperparameter optimization with just a few lines of code, as shown here. But we've highlighted in blue the ability to define a multitask experiment by defining the tasks. So here in this case, there's three tasks based on the number of epochs the deep learning model has been trained for. One that's a 1/10th cost, one that's a 4/10th cost, and one that's the full cost model. Then, during hyperparameter optimization, SIGOP will trade off exploring the problem with the cheapest cost tasks to learn about the problem space, and then exploiting that information and using the full cost task to find solutions that you can productionize. Once you've run the experiment, you can look up its performance on the web. So these are screenshots from our product, but I'll note that we're not sharing any real data from real customers because that's, of course, proprietary. These are internal benchmarks that we ran. This plot shows the accuracy of the model on the y-axis, along with on the x-axis one of the parameters being tuned. As you can see, the partial cost tasks in gray vary wildly in performance, but they do seem to line up with this cluster near about 0.2, where we start to find the high-performing tasks. And that's where the blue full cost tasks are sampled to find this cluster of good solutions at a reduced cost. You can also see how the model improves over time. So this is on the x-axis how many different models have been trained. So we start with about the first 20 trials and we get to a accuracy of about 0.72. This is all done with the partial cost tasks at a more efficient rate. Then we start to sample the full cost tasks, and that's where we start to refine from the information we've seen and get to a great solution. And you can also see the distribution of tasks across costs. So this is where you see that the cheapest task on the right is sampled the most frequently, and this is what we typically see because it's the cheapest and thus typically the most efficient way to gain information about the space. But then on the left, we see how many times the full cost task was sampled. And this is where we find the solution we typically want to productionize. So the research from the University of Freiburg was a great inspiration for us, but we wanted to use this information, this opportunity, to benchmark the performance of these methods in an applied setting. So we could make good recommendations to our customers about which of these models is going to perform best for their use case. So recall that for multitask optimization, the goal is not strictly to find the best solution, but it's to find a good solution in a greatly reduced amount of time. So in this case, we tested a convolutional neural net, which has 10 hyperparameters. And our goal was to find a good solution in the time it would take to train 25 full cost models. So we ran across a variety of techniques: random search, early termination, and multitask optimization. So what we observed in this case is that random search and hyperband both performed pretty similarly, and we're able to find something in the 0.72 accuracy range. And that multitask optimization significantly outperformed both. And these improvements were consistent across multiple dimensions. So for hyperband, what we did was we tried different numbers of rounds of successive halving, which is basically how many times you reduce the pool of available models. And for multitask, we also evaluated with different numbers of tasks. And in both cases, we evaluated with different degrees of parallelism. And the parallelism is how many models are you training at the same time. And across all these different cases, we saw this improvement with multitask of about 7 percentage points. And this is a pretty big difference. It can really be the difference between whether a deep learning model does or does not make a big impact on your business. So that's all I have to talk about for the tuning and training efficiency, and let's switch gears a little bit to turn to a new problem. How can teams with relatively few resources manage their clusters efficiently for these complex models? In many cases, cluster management and efficient parallelization can generate high-quality models in significantly less wall clock time. Now, this is not always a challenge. For simple use cases where you have a model that trains quickly and perhaps can complete on your laptop, the DevOps challenge for this does not really exist. But for a lot of our customers, this isn't the case. There's typically multiple compounding levels of complexity. So if you're a team of modelers, you have multiple users who are all trying to share the same resources for their model training. Each of those users might have several experiments that they're trying to run in parallel. Each of those experiments might require them to train multiple versions of the model at the same time. And then finally, each individual model evaluation might also need to be parallelized across multiple GPUs. So it's this multiple compounding levels of complexity, while the amount of compute capacity that's typically available to the team is fixed. As you can see, the levels of complexity compound and present a very unique DevOps challenge for these teams. So when this complexity is introduced, a lot of problems come up about infrastructure, dependencies, logging, tracking metadata. So we wanted to abstract all this away for our users in a command line tool to manage this problem. We call it SIGOP Orchestrate. And how it works is it uses Docker to containerize your models and Kubernetes to execute them in parallel on your compute cluster. This has many advantages, but the most notable is that it provides a stable, scalable way to submit training jobs to your cluster and have them scheduled and executed in parallel. So Orchestrate makes this simple. First, use the command line to launch a cluster of machines on your favorite cloud that you or your team will use to run your experiments. Second, you schedule optimization experiments to get distributed to your cluster, which runs the containerized version of your model across your available machines. This automatically integrates with our existing API to conduct hyperparameter optimization to get you to the best version of your model as possible. And then finally, you can monitor your experiments on the web to watch how they progress, see how your underlying infrastructure is being used, and have a better understanding of your optimization progress. The goal of all of this is to fully abstract the infrastructure away from the modeler so that they can focus on what they do best, and that's modeling. So our goal is to make it pretty easy to integrate it into your existing modeling process. I'll show you how that works. So this code should look pretty familiar. This is a pretty standard random forest model. But what we've done here is in the kind of first highlighted box is we've replaced the parameters that you intend to optimize, the ones you want to search for different values of to find the best version of your model, with calls to orchestrate. And then at the end of the code, I've highlighted where we report the metric that you're trying to optimize, which is in this case the model accuracy, to orchestrate. The goal of all this is to be as frictionless as possible so it fits into your existing code with as few modifications as possible. You'll also define a model configuration file, and this is where you define those parameters and how you intend to search them. So in this case, they're types. Some of these are integers. Actually, in this case, they're all integers, but they can also be floating point or categorical parameters, which means you're choosing from a set of possible values. And you can define the bounds. This is the area over which you're trying to search to solve this problem. You also specify how many models you intend to train and also the degree of parallelism. You can run multiple optimization experiments on the same cluster. So you use the SIGOP run command to containerize the model, submit it to your cluster, and start executing. All the dependencies and setup are already included and packaged into the container. Then the experiment's begun. You can close your laptop and walk away and come back when the optimization is concluded. Offer additional capabilities. You can use the CLI to monitor the status of your experiments. You can see how far they've progressed and if there have been any failures. You can follow the logs to watch for errors or to watch the progress of a single model evaluation. And then finally, all the results are available on the web. Use this page to find the best results so far, how your infrastructure is being used, to monitor the experiment improvement, and more. So going back to these two problems, if you implement multitask optimization and automated cluster management, you're solving two of the biggest challenges for deep learning optimization. This will set up your team to optimize expensive models that previously may have taken too long to tune. And by optimizing more of your deep learning models, you're taking a huge step for your team in increasing the likelihood that you're going to have high-quality models that make it to production. So if we go back to this case study we had at the beginning, using multitask optimization, you may be able to reduce the training time for a single evaluation, perhaps to 4 hours on average. That translates now down to 20 days of training time instead of 60. But by using efficient parallelization, you could split this across 10 machines and get this down to 2 days of wall clock time. And this is how you would translate advanced optimization into real value for your team. You no longer have to wait 60 days to solve this problem. You have your answer in 2. If you're interested in more detail on this or any of the other optimization challenges that we research, they're available on our blog, which I encourage you to check out. We have a lot of great research and product posts from our team about how we're solving these complex challenges. And our engineers provide detailed insights on their experiments and the research that they're doing. So thanks for your time. Whether you're a researcher, a business, or an academic, there's a version of SIGOpt that's available for you. And if you're interested in trying out SIGOpt Orchestrate or multitask optimization, come talk to me or some members of my team who will be joining me shortly, and I'd be happy to help out. And of course, we're always hiring, so if you're interested in a career where you're interested in doing research on the most cutting-edge optimization techniques, you can check out our website or come talk to me afterwards. That's all that I have to talk about today, but I'm here to answer any questions. Thank you.
We are open for the Q&A. Anybody? Okay. Hi. So when you say a partial cost model, what do you mean? Like, can you give an example? Maybe a CNN?
Yeah, so if we go back to all the way back. Yeah, so in this case, if you have your SVM model, to train it on the full data set might take, let's say, an hour. But if you train it on a fraction of the data set, in this case, 1/4, 1/16, or 1/28, it'll take proportionally that much less time. So if indeed that you can learn from those partial cost evaluations, then you can possibly, using the advanced techniques like multitask optimization, get results that will inform your optimization progress in significantly less time. Yeah, the question was, is it just a smaller data set, or are there other methods for this? Well, really any method that has the property that the smaller cost evaluation correlates with the full cost evaluation will have this property. And what we found in practice, the 2 best ways to obtain that are using subsamples of the data set, like I mentioned, or if it's a deep learning model, training it for fewer epochs. What I wouldn't recommend, for example, is using an entirely different model that would be cheaper to evaluate, because that's not really going to tell you anything about the performance of the full cost model.
So when you subsample the data sets, what kind of, you need to look out for a distribution, or just randomly do it?
Will you be able to repeat the question for the video?
Yeah, the question was, when you're subsampling the data, what's the best method for that? Yeah, I typically recommend random so that you're not introducing any bias, but some sort of random subsample would work pretty well, which I believe is what they did in this paper.
Okay.
What kind of a platform do you support, like a Spark, AWS, that kind of thing? What kind of solution do you provide if we're on those platforms?
Could you repeat the question? Sorry.
For you're optimizing the deep learning model, right? First of all, what kind of deep learning platform you support? What kind of cloud platform you support? What kind of pipeline you support?
Yep. So we are a totally black box solution, so we support models of all types. If you're doing, and the reason for that is because the model is still executed on your infrastructure. At SIGOpt, we never look at your model code, and we never look at the data, your training data, because that's typically proprietary to you or your team. So you interface with our API to receive suggestions for versions of your model to evaluate, and you evaluate those suggestions, and you report back to us how well they did. So we work across all these different platforms, whether it's Spark, whether it's AWS, whether it's an on-premises solution, and we also work for different model types as well.
So is that just by your library put in my code and then?
So it's our library is we have a Python client-side API library, but that talks to our API, which is hosted.
What do I need to send to your API? Is that my data or what? What kind of thing I need to
Yeah, so if we go back to this slide, this is the type of information that's sent to SIGOP. So basically, the parameters you have available in this random forest model, you would say, I'm training a random forest, it has this many features. Oh, I'm trying to optimize the max features, n estimators, min samples, leaf parameters. They're integers, and these are the bounds. And then SIGOP uses that information to conduct hyperparameter optimization. So we never see your model code, and we never see your data. But you'll submit requests to our API for suggestions that fit these bounds. You evaluate those suggestions, and then you use our API to report back how well those suggestions did.
Thanks.
We have one over here.
So what's your method of like showing the simple tasks, like the low cost tasks, somewhere correlated with the full cost tasks?
What's our method
for like show there's a correlation or somewhere correlated, and then at least you will overcome once you factor into the cost, it's actually beneficial.
Yeah. So if you follow the strategies I recommended for choosing that, how you choose those tasks, in practice that typically performs very well. During the optimization process, we do try to analyze and figure out what that correlation is between those tasks. If throughout optimization we learn, actually these tasks are not correlated as well at all, we can still conduct optimization in the full cost task setting. It just takes additional time for us to learn enough information to determine that they're uncorrelated. So specifying tasks that are not well correlated doesn't mean you won't get to a solution. It just means it might take longer than if you had appropriately chosen those tasks.
Anybody more from behind, if I can't see you? We do have 20 minutes more. Okay.
Hi, I apologize. I missed a major section of the presentation, but I was outside at your booth as well, and I was interacting with somebody. So my question is basically, it's difficult for me to wrap my head around the fact that you're saying that you don't access my code, you don't access my data, but then how exactly, like, I fail to understand how exactly will this work? Like, what do you do in the background that's actually beneficial to me? Like how do you actually even suggest what I need to do, even without knowing what I'm trying to do?
Yeah, I think I'm trying to see if I have a additional slide for this, which I don't believe I do. But yeah, so the only information that SIGOP sees is the parameters that you are trying to optimize, right? So in that sense, it's black box optimization. All we need to do is present it with the variables. These are the variables that we have available to optimize. We make suggestions, and then you as the customer take those suggestions, evaluate them, train that model, the suggested model on your own infrastructure, compute the metric you care about, let's say accuracy, and then you report that metric back to us. So that's the only information we see. For the parameters we suggested, how well did that perform for your metric? And that's all the information we need to build our own optimization model of what we think is going to make your model perform the best.
So basically, I'm outsourcing my thinking process to this. Does that mean?
You're outsourcing what to this?
I'm outsourcing my thinking process, right? I don't need to think anymore, like what I need to do next. Is that what it is?
I wouldn't say that. But basically, this hyperparameter optimization is really just one part of the modeling pipeline. As you as the modeler, what I want you to be focusing on is which data sets should I be using? Which algorithm should I be using? How is this going to directly affect my business? Focusing on the parts of the problem that you as the modeler are the expert in. This optimization, while important in order to get to the best version of your model, isn't a great use of your time as a modeler. So using SIGOP for this portion of the process so that you can focus on what you're best at as a human expert data scientist, which is the modeling.
Any more questions? We definitely have a lot more time.
I'll be around. I'm happy to answer questions one-on-one or chat more in depth with anyone else.
You good?
All right. Thank you, everyone.
Thank you. Thank you very much.